So in lecture 23 of number theory, I began to talk about the subject of what are called quadratic residues. And as with a lot of number theory, it starts with solving equations. And but in number theory, often we are interested in solving equations modulo p, where p is a prime number. And for linear equations, we have a theorem that tells us everything. If you have ax congruent to b mod p, and a and p are relatively prime, if a and p were not relatively prime, a would be 0 mod p, and you wouldn't have an x term at all. So this is only a linear equation if a is not 0 mod p, and this linear equation always has a unique solution modulo p. So if you had, for example, 6x congruent to, I don't know, 11 mod 13, there has to be a unique solution modulo 13. And it's just a matter of maybe trial and error until you find it. Here's a sneaky way to find a solution. 6 times 2 is 12, which is congruent. So solution, 6 times 2 is 12, which is minus 1 mod 13. So if you multiply this equation by minus 11 or by 2, 6 times 4, I'm just multiplying by 2, multiply by 2, is congruent to minus 2, which is the same as 11 mod 13. So here we have the solution. The solution is NEX congruent to 4 mod 13. And if you want to check, 6 times 4 is 24. 24 minus 11 is 13. So congruent to 0 mod 13. But the whole point is that for a linear equation modulo a prime, there always exists a unique solution. So after you've studied linear equations, what's the next case? Quadratic equations. So you might want to solve an equation ax squared plus bx plus c congruent to 0 mod p. That's a quadratic equation. And how can you solve? And quadratic means that the leading coefficient a and p are relatively prime. Otherwise, this would be 0, and you would just have a linear equation. So I looked at an example. We can look at an example. Suppose we have 8x squared plus 3x minus 2 congruent to 0 mod 11. We want to solve this equation for x. So you might do what you learn in pre-calculus or high school algebra. You simplify the equation by completing the square. What that means is multiply through by 8 and then try and get a perfect square somehow in this equation. So if you multiply through by 8, you get 8 times 8x squared plus 3 times 8x minus 2 times 8 congruent to 0 mod 11. Any solution of this will be a solution of the original quadratic. 8 times 8 is 8 squared. This is like 8x squared plus 24x minus 16.
Why you chose 8?
Because the leading coefficient is 8, and I wanted to get a square here in the first term.
Oh, okay.
Okay. And of course, mod 11, this is the same as 8x squared. Mod 11, 24 is 2. And mod 11 minus 16 is minus 5, which is the same as 6. So I have this, all right, but I want to get a perfect square somehow in this. So what can I do? So you have to remember, if you have, let's see, ax plus b squared, this is a squared plus 2abx plus b squared, right? That's, you square this quadratic, this is what you get, ax squared, 2abx plus b squared. So in this looks like my a. So just look at this and compare it to this expression. It would be like a is going to be 8x. And I want 8 is 8, right? The coefficient, a squared x squared, right? A squared x squared plus 2abx plus b squared. So, or just to do this a little more neatly, when you square ax plus b squared, you get the square of the first term, ax squared, plus 2abx plus b squared. So here ax is 8x, so a is equal to a, and I want to get choose a b such that I have 2ab is congruent to 2 mod 11. So let's see, what can I do? I have 8x squared plus, let me write 24x as 16x plus 8x, and minus 16, which is the same as 6. This is all mod 11. 6 is the same as 1 plus 5. So you just have to check that this equation is the same as this. This is 8x squared. 16x plus 8x is 24x. 1 plus 5 is 6, which is the same as congruent to minus 16 mod 11. And then if I look at this, this is exactly 8x plus 1 squared. And here I have 8x plus 5. Maybe I should have picked an easier example, but 8x plus 5 is 8x plus 1 plus 4, congruent to 0 mod 11. And so suppose I let y be equal to 8x plus 1. Then this equation becomes y squared plus y plus 4, congruent to 0 mod 11. and which is the same as y. 1 times y is the same as 12 times y, plus 1 is congruent to 12 mod 11. So y squared plus 12y plus 4 congruent to 0 mod 11. I'm just trying to get squares somehow appearing in this. This is y squared plus 2y plus 1 plus 10y plus 3. And this is y plus 1 squared. Let's see, is this going to be right? Certainly not going to be wrong. I want to get this to be a perfect square. Let me do it better. This is y squared. So let me get a clean sheet of paper. I started with the quadratic equation 8x squared plus 3x minus 2 congruent to 0 mod 11. And I want to solve it. So I could rearrange this as, or multiply by 8 and rearrange. I get 8x squared plus 2x plus 6 congruent to 0 mod 11. And this turned out to be exactly the same as 8x plus 1 squared plus 8x plus 1 plus 4 congruent to 0 mod 11. I just change variables to simplify everything. That y equal 8x plus 1. So this is y squared plus y plus 4 congruent to 0. Mod 11. I can write this as y squared plus, so 1 is congruent to 12 mod 11. So 1 times y is the same as 12 times y. And 4 is 36 minus 32. So I can write this as plus 36 minus 32, and mod 11, this is congruent to let me just write it. Minus 32 congruent to 0 mod 11. But this now is a perfect square. This is y plus 6 squared minus 32 congruent to 32, which is the same as congruent to 32, which is minus 1 mod 11. So let me make another substitution. Suppose I let z equal y plus 6. Then we need to solve z squared congruent to 1 mod 11. So if you can find the z that's congruent to 1 mod 11, z is y plus 6, and y is 8x plus 1 plus 6, so 8x plus 7. So if I can solve for z, then x, then you simply solve this equation, 8x plus 7 congruent to that number z mod 11. So we've started out with this equation. And by doing what is basically high school algebra, we get an equation of the form z squared congruent to minus 1 mod 11. Solve that equation. And so you can check. Check. Just plug in z equal 1, 2, 3 up to 10. look for a solution. What do you find? No solution of this congruence. So therefore, there's no solution of the original equation. So some quadratic equations have solutions, some quadratic equations don't. This is just like the situation in elementary algebra. If you had to solve the equation x squared equal -1 in the real numbers, there's no solution, right? Because in the real numbers, the square is always positive or 0. So similarly, mod p, a quadratic equation, may or may not have a solution. Let's do an experiment. Suppose we want to try and solve this equation, not mod 11, but let's try and make it easy, mod 5. So suppose we have to solve x squared plus 3x minus 2 congruent to 0 mod 5. Now, in some sense, this is a lot easier because we could just plug in 1, 2, 3, 4, 5 and look for a solution. But let me try and do what I did before and complete the square. So first of all, I can simplify this a little bit. 8x squared is the same, 8 is congruent to 3. So this is 3x squared plus 3x minus 2. Minus 2 is the same as plus 3, congruent to 0 mod 5. Because 3 is 3, minus 2 is 3, and 8 is 3 mod 5. So this is the same as 3 times x squared plus x plus 1, congruent to 0 mod 5. And if this has a solution, 3 is relatively prime to 5, so x squared plus x plus 1 is congruent to 0 mod 5. We have to look for a solution of this equation. Let's see. Let me
Professor, how did you get 3x squared plus 3x plus 3?
So from here to here, 8 is congruent to 3 mod 5, right? So I can replace 8 by 3. Minus 2 is also congruent to 3 mod 5. So I can replace minus 2 by plus 3. Because these are congruences, mod 5. And I can factor out the 3 and get this. Let's see. How can I complete the square? If this were even, it would be easier. So we know that 1 is congruent to 6 mod 5. So I'm going to write this as x squared plus 6x plus 1 congruent to 0 mod 5. I can complete the square by adding 9 to both sides. Plus 9 plus 9. And now x squared plus 6x plus 9 is x plus 3 squared plus 1 congruent to 9 mod 5. So I want to solve x plus 3 squared congruent to 8. 8 is the same as 3 mod 5. Suppose I let y equal x plus 3. So I've reduced this to a pure quadratic. Solve the equation y squared congruent to 3 mod 5. And I mean, actually, let's just make a table. Here's y, and this is y squared mod 5. 0, 1, 2, 3, and 4. If I let y equal 0, y squared is 0. If y is 1, y squared is 1. If y is 2, y squared is 4. If y is 3, y squared is 9, which is the same as 4. If y is 4, y squared is 16, which is the same as 1. So a square, you don't see a 3 over here. So this equation also has no solution. Huh. That's bad luck for us. We're trying to solve these quadratic equations, and they don't always have a solution. But in these first two examples I picked, don't have a solution. But the moral of the story is by completing the square once or twice or as many times as necessary, you can always get an equivalent congruence that has the same solutions as the original quadratic equation of the simple form x squared congruent to a mod p. So our goal to solve quadratic equations, we just have to know when you can solve this kind of congruence. Sometimes it has a solution, sometimes it doesn't. So let's look at some examples. Suppose we take p equal to 5, right? So this is like, what does it mean to say x squared is equal to a? This is like x is the square root of a, because you square x, you get a. So this is just finding square roots if they exist. So for p equal 5, we already worked out a table. We had, for every a, what is a squared mod 5? So 0, 1, 2, 3, 4 are the congruence classes mod 5. When we squared them, we got 0, 1, 4, 4, and 1. So x squared congruent to 0 mod 5 has the unique solution x a, or x congruent to 0 mod 5. X squared congruent to 1 mod 5 has two solutions. X congruent to 1 or 4 mod 5. X squared congruent to 2 mod 5, no 2 there, has no solution. X squared congruent to 3 mod 5 has no solution. And x squared congruent to 4 mod 5 has two solutions. X congruent to 2 or 3 mod 5. So we introduce a symbol to tell us whether or not this congruence has a solution. So we have the equation or the congruence x squared congruent to a mod p. So we define what is called the Legendre symbol. A over p in parentheses. So this is defined to be 1 if a and p are relatively prime and x squared congruent to a mod p has a solution. -1 if a is relatively prime to p and x squared congruent to a mod p has no solution. And 0 if p divides a.
Recording in progress.
So this is so for p equal to 5, we just computed the Legendre symbol. 1 over 5 is 1. because because 1 has a square root. 2/5 is -1, 3/5 is -1, and 4/5 is +1, and 0/5 is 0. So, and there's a language we use, which is A is a quadratic residue mod P if A is relatively prime to P and x squared congruent to A mod P has a solution, is solvable. So we have this basic simple quadratic equation, x squared congruent to A mod P, A relatively prime. If A is 0 mod P, this always has a unique solution, 0. 0 squared is 0. So this is only interesting when A is non-zero mod P. And in that case, this may or may not have a solution. If it does, A is called a quadratic residue mod P, if you can solve this, and A is called a quadratic non-residue mod P if A and P are relatively prime and x squared congruent to A mod P has no solution. So 1 is a quadratic residue mod 5, 4 is a quadratic residue mod 5, 2 is a quadratic non-residue mod 5, and 3 is a quadratic non-residue mod 5.
Non-residue is the -1?
Yes, so A/P is 1 if you have a quadratic residue, because you can solve the congruence. A is a quadratic non-residue if A/P is -1, because that means you cannot solve the congruence. So this is just...
And if it's 0 is...
Sorry?
And if it's 0 is what?
So if A is 0, it's not interesting. If A is 0, you can always 0 squared is always congruent to 0 mod P. So if A is 0, there's a unique solution, 0 squared congruent to 0. And you don't say 0 is a quadratic residue or non-residue. It's just like saying every number is positive, negative, or 0, right? 0 is not positive, 0 is not negative, 0 is 0. So with respect to quadratic residues, the non-zero numbers mod P are either residues or non-residues, and 0 is neither a quadratic residue nor a quadratic non-residue. It's just like saying the number 0, the real number 0, is neither positive or negative.
Okay.
You can also say a couple of other things. So x squared congruent to A mod P is the same congruence as x squared minus A congruent to 0 mod P. Right? Just bring the A over to the other side. This is a quadratic polynomial. This is like saying f of x is congruent to 0 mod P, where f of x equals x squared minus A. This is a quadratic polynomial. And we can make two quick observations. If x squared is congruent to A mod P, then minus x squared, you square minus x, you get x squared, is also congruent to A mod P. we're only looking at P an odd prime. Because when P is equal to 2, there's nothing to say. For P equal 2, 1 squared is 1. So 1's a quadratic residue. That's all it is. So for P an odd prime, if X is a solution, so therefore f of X congruent to 0 mod P, if and only if f of minus X is congruent to 0 mod P. And f of X, which is this polynomial x squared minus a, is a quadratic. It has degree 2. So, and the integers mod p form a field. So this congruence has at most 2 solutions, which means what? If x is not 0 mod p, then or let me put it this way. If x is congruent to minus x mod p, if x and minus x are congruent mod p, bring this to the other side, then 2x is congruent to 0 mod p. So p divides 2x, but p is odd, it doesn't divide 2. So x is congruent to 0 mod p. So the only time x and minus x are congruent to 0 mod p is when x is 0. So that says that f of x equal x squared minus a has either, this is where a is not 0 mod p, has either 2 solutions or no solution. Those are the only possibilities. Now, if you take an odd prime p, that's 2k plus 1, let's say it's an odd number, then p minus 1 is 2k. So you have 2k congruences, x squared mod p, where x is not 0 mod p. So the x can run through 2k numbers, and x and minus x are the same when you square them. So there are exactly k quadratic residues mod p, and there are exactly k quadratic non-residues mod p. And what is k? K is p minus 1 over 2. So all I'm saying is, let's look at an example. Suppose we take p equals 7. So what are the numbers that are not 0 mod 7? I could take x to be 1, 2, 3, 4, 5, or 6. And what is x squared mod 7? 1 squared is 1. 2 squared is 4. 3 squared is 9, which is congruent to 2. 4 squared is 16. Let me just write 2 here. You square 3 mod 7, you get 2. 4 squared is 16. 16 mod 7 is 2. 5 squared is 25. 25 mod 7 is 4. 6 squared is 36. 36 mod 7 is 1. So when I square the numbers, I get 1 twice. X squared congruent to 1 mod 7. What are the solutions? X congruent to 1 or 6 mod 7. X squared congruent to 2 mod 7. What are the solutions? X congruent to 3 or 4 mod 7. x squared congruent to 4, mod 7, x can be 2 or 5, x congruent to 2 or 5, mod 7. Each of these congruences has two solutions. And what about the other numbers, mod 7? X squared congruent to 3, 5, or 6, mod 7, no solution. So for mod 7, these are the Legendre symbols. One over 7, 2 over 7, 4 over 7 are plus 1. 3 over 7, 5 over 7, and 6 over 7 are minus 1. So that's the complete story about quadratic residues, mod 7. Let's take another case. Let's take P equal 11. And we want to compute A over 11 for all A. So for A, not congruent to 0, mod 11. So what are the numbers not congruent to 0, mod 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10.
10.
Those are the non-zero congruences, mod 11. And I want to compute A squared, mod 11. 1 squared is 1. 2 squared
It's 4.
is 4. 3 squared,
It's 9. So it's
9.
2.
4 squared
16.
is 16. Mod 11 is what? It's 5.
Wait, why is 3 square? 3
3
square is
squared
9,
is 9.
but 9 is also 2 mod 11, right?
No, it's negative 2.
Oh, okay.
What is 5 squared, mod 11?
5 squared is 25. 25 is what? Is it 3 mod
3,
11?
yeah. 5 squared is 25. Minus 22 is 3.
Oh,
What
I
is-
did 25 minus 11 is 14, and then 14 minus 11 is 3.
You can do it in 1 step or 2 steps, but the answer is going to be 3, no matter what.
Okay.
What is 6 squared, mod 11?
36. 25. So is it also 3?
Yeah.
No.
What is 7 squared, mod 11?
7 squared is 49. Mm, mm, 27. Mm. Is it 4?
7 squared is 49. 49 minus 4 times 11, 49 minus 44. What's 49 minus 44?
5.
Yeah, that's what it is. What's 8 squared mod 11?
8 squared is 64 minus is it 2 mod 11?
Let's see, 8 squared is 64.
Mhm.
Let's see. Eight squared is 64, which is 55 plus 9, which is 5 times 11 plus 9. So 8 squared is going to be congruent to 9,
Wait, why you did 55? I'm
because it's
still.
5 times 11.
So you always takes the last number and times 11?
Well, I don't know what you mean. No, I don't know what you mean by the last. No, it's not the last number. You want to know, like you have a number 64. You want to divide by 11. When you divide by 11, you get 11 times 5 plus 9. So the least non-negative residue of 64 mod 11 is 9. If you had a number like, I don't know, 72, divided by 11, this is 11 times 6 plus 6. So 72 is congruent to 6 mod 11. This is just how you find the least
Oh,
non-negative residue of any congruence class. What is 9 squared mod 11? What is 9 squared equal to?
It's 81.
And if you divide 81 by 11, what's the remainder?
This 77. Oh, that's not. So 89 is 8 times 10. No, if we do 8 times 11,
Forget
it's
about 10. Just take 81 and divide it by 11. What's the remainder?
Is it 1?
Wait. I mean, all I'm asking you to do is 8 into 11. Sorry, 11 into 81, right? Just do long division. What is 11 into 81?
8.
No,
Wait.
8 times 11 is 88. That's too big.
Oh, yeah. That's why I'm confused. I was doing 89. It's 81.
When you divide 11 into 81, what's the quotient?
7.
7.
Mm.
What's 7 times 11?
77.
What's the remainder?
4.
So when you do long division, 81, when you divide 81 by 11, this is 81 times 7 plus 4. So, and this is 9 squared is 81. So 9 squared is congruent to 4 mod 11.
Okay, I see.
What about 10 squared? What is
Uh,
10 squared congruent to mod 11?
10 squared is 100, and 109 times 11 is 99 plus 1.
So
Right?
what's the remainder?
1.
1. Yeah, okay. So these are the non-zero congruence classes mod 11, 1 through 10. When you square them, you get these 10 numbers. And you notice there are only 5 different numbers, 1, 3, 4, 5, and 9, and each occurs twice. In fact, if you look at the first 5 numbers and the next 5 numbers, you go 1 to 3, 1, 4, 9, 5, 3, and then you go backwards the same way. This kind of symmetric.
Oh, yeah.
All right. And in
Good.
terms of the Legendre symbol,
Okay.
when is Legendre symbol plus 1? The squares that you get are 1, 3, 4, 5, and 9. So 1 over 11, 3 over 11, 4 over 11, 5 over 11, and 9 over 11. These are all equal to 1. Those are the quadratic residues. These are the numbers that have square roots. And the numbers that don't appear here don't have square roots. The numbers that don't appear here are 2, 6, 7, 8, and 10. So the Legendre symbol for 2, 6, 7, 8, and 10 is -1. The Legendre symbol for 1, 3, 4, 5, and 9 is +1. So this is the same as saying, for example, if you take x equal, if you take 6, x squared congruent to 6 mod 11 has no solution. Because no matter what number you square, you never get a 6 here. And the same with 2, 7, 8, and 10.
So the 1, 3, 4, 5, and 9 are the
Are the quadratic residues. So if you want to solve x squared congruent to, let's say, 4 mod 11, there are 2 solutions. X congruent to 2 mod 11 and x congruent to 9 mod 11. So this congruence has 2 solutions, mod 11. This congruence has no solution.
okay. Okay. Let's see.
Now, so this is the moral of the story. To solve a quadratic equation, ax squared plus bx plus c congruent to 0 mod prime, you can always reduce to a simple quadratic equation, or it's really a quadratic congruence, reduce to a congruence of the simpler form, x squared congruent to a mod p. And to know if this has a solution, you just compute the Legendre symbol. A over p. If this is +1, this congruence has a solution. If the Legendre symbol is -1, the congruence has no solution. And So we want to be able to calculate the Legendre symbol. So the first theorem in this regard, and I still have to copy the notes for this section and put it on Blackboard, is the following. For any odd prime P, the Legendre symbol A over P is always congruent to A to the P minus 1 over 2 mod P. So let me just look at an example of this. Suppose I take P equal to 11, and I want to calculate the Legendre symbol 2 over 11. Well, I want to calculate this Legendre symbol. So the theorem says that 2 over 11 is, so here A is equal to 2. So this is, and if P is 11, P minus 1 over 2 is 11 minus 1 over 2. That's 10 over 2. That's 5. So 2 over 11 is going to be congruent to 2 to the power 5 mod 11. 2 to the 5th is 32. 32 is minus 1 mod 11. So 2 over 11 is minus 1. All right, so this is plus minus 1. This is minus 1. So 2 over 11 is minus 1. So 2 is a quadratic non-residue, and x squared congruent to 2 mod 11 has no solution, because this is minus 1.
Mhm.
Suppose I want to calculate 3 over 11. We want to know whether 3 is a quadratic residue mod 11. So by this theorem, 3 over 11 is congruent to 3 to the 11 minus 1 over 2, 3 to the 5th, mod 11. What is 3 to the 5th? So what are the powers of 3? 3, 9, 27, 81, 243. What is 243 mod 11? This is in fact congruent to 1 mod 11. Why? Because I'll take the 11 into 243. This goes twice, 22, 23. This goes twice, 22. Leaves a remainder of 1. So 3 over 11 equals 1. And x squared congruent to 3 mod 11 has a solution. It's solvable. And in fact,
So
one
it
solution
only
is
has to be like 1 and negative 1, right?
the
To be
Legendre symbol is
valid.
always 1 or negative 1.
Okay.
And in fact, one solution of this is 5, because 5 squared is congruent to 3 mod 11. And so minus 5, which is 6, is also congruent to 3 mod 11. So if the congruence, if this quadratic congruence has a solution, it has exactly 2 solutions, and the 2 solutions are x equal 5 and x equal 6.
Okay.
Let's see. Let me just make one other comment to suggest why this theorem makes sense. The theorem says that A over P is congruent to A to the P minus 1 over 2 mod P. So again, P is always an odd prime, and A and P are relatively prime integers. So if you take A, suppose I let X equal A to the P minus 1 over 2, then X squared is A to the P minus 1 over 2 squared, which is A to the P minus 1. And if A is relatively prime to P, A to the P minus 1 is always 1 mod P by Fermat's theorem. But if X squared is 1 mod P, then X can only be plus or minus 1 mod P. Because the equation X squared equals 1 or congruent to 1 mod P can't have more than 2 solutions, and plus 1 and minus 1 are the 2 solutions. So this number on the right-hand side of this congruence is always plus 1 or minus 1. So to prepare for this, remember, every prime number P has a primitive root, call it G. That means if A is not 0 mod P, then the powers of G give you every number not 0 mod P. A is congruent to G to the K mod P for some unique K between 0, 1, 2 up to P minus 2. And K is called the index of A mod P with respect to the primitive root. And so we can actually state a nice theorem or observation. So G, a primitive root mod P, A and P relatively prime, then A is a quadratic residue mod P if and only if the index of A mod P is an even number. That is, to say the index of A, supposed to be let K be the index of A. That means A is congruent to G to the K mod P. If K is an even number, K equal 2 times L, then A is congruent to G to the K, which is G to the 2L mod P, and G to the 2L is G squared, it is G squared to the L. Let me write it like this. This is K is L times 2, so this is G to the L times 2, which is G to the L squared, which is X squared, for X congruent to G to the L mod P. So if K is even, if the index of A mod P is an even number K, then A is a quadratic residue, A over P is plus 1. Right? And if K, now this already gives you was half, so half of, so these indexes K, this is a number between 0, 1, 2 up to P minus 2. I have P minus 1 numbers here. Half of them are even, so they're P minus 1 over 2 even numbers. So, and they're only P minus 1 over 2 quadratic residues. So if K is odd, then A over P is minus 1. So the index of a number mod P determines whether or not it's a quadratic residue. So let's see, how can we prove the theorem? I want to prove that A over P, the Legendre symbol, is congruent to A to the P minus 1 over 2 mod P. So suppose that A is congruent to G to the K mod P. So if A over P is 1, if the Legendre symbol is 1, that means the index K is even. So K is 2L, which means A to the P minus 1 over 2, A is congruent to G to the 2L to the P minus 1 over 2. The 2's cancel. This is G to the P minus 1 times L. G to the P minus 1 is 1, so this is 1 mod P. So if A over P is 1, A to the P minus 1 over 2 is 1. And if A over P is minus 1, that means that K is an odd number. K is 2L plus 1. And that means that A to the P minus 1 over 2, which is, what is A? A is G to the 2L plus 1 times P minus 1 over 2. This is G to the P minus 1 over 2, and that's minus 1 mod P. Because if you square this, you get plus 1. So this is not, the squared is 1, and it's not plus 1, so it's minus 1. All right. So part of what we need to learn is how to compute the Legendre symbol. So here are some rules. Suppose I have a product of two numbers. Let's see how this works. So AB over P this is congruent to AB to the P minus 1 over 2 mod P, which is the same as A to the P minus 1 over 2, B to the P minus 1 over 2. This is congruent to A over P, and this is congruent to B over P. So this number is congruent to this number mod P. These numbers are both plus and minus 1, so they have to be equal. So A over B over P is A over P times B over P. So this allows us to reduce maybe a hard problem to a simpler problem. Suppose I wanted to solve, for example, I want to know what is 21 over 41? Is 21 a quadratic residue mod 41 or not? So 21 is 3 times 7. And by this rule, this is 3 over 41 times 7 over 41. And it might be easier to compute these two simpler Legendre symbols than to compute this one. So this is a very important rule for computing that's helpful to compute Legendre symbols. What about the congruence x squared congruent to minus 1 mod P? Sometimes this has a solution and sometimes it doesn't. So for example, x squared congruent to minus 1 mod 5 has the solution x congruent to 2 or 3 mod 5. What about x squared congruent to minus 1 mod 7? Well, you can square all those numbers mod 7 and you'll never get minus 1. This has no solution. And it would be nice to know when you can solve this congruence. And there's a simple rule. It says minus 1 over P. When is minus 1 a quadratic residue mod P? When can you find the square root of minus 1? This is equal to 1 if and only if your prime is congruent to 1 mod 4. I mean, if you take a prime number and divide by 4, you get a remainder of 1 or 3. Minus 1 over P is minus 1 if and only if P is congruent to 3 mod 4. We're only looking at odd primes. Any number that's odd, if you divide by 4, gives you a remainder of 1 or 3. P is 1 mod 4, minus 1 has a square root. If P is 3 mod 4, minus 1 has no square root. 5 is 1 mod 4, minus 1 has a square root. 7 is 3 mod 4, minus 1 has no square root. So this is a very useful rule. And there's a similar rule for knowing when 2 is a quadratic residue. And the rule says the following: 2 is a quadratic residue mod P if and only if P is congruent to 1 or 7 mod 8. Let's look at some examples of that. Suppose I take P equal to 17. 17 is congruent to 1 mod 8. So x squared congruent to 2 mod 17 must have a solution. Knowing it has a solution is easier than finding a solution. Right? By this rule, we know this congruence has a solution. How do we find it? Well, actually, I can be kind of lucky. If I let x equal to 6, x squared is 6 squared is 36, and 36 is congruent to 2 mod 17, because 36 minus 2 is 34, is 2 times 17. And if 6 is a solution, then x equals 17 minus 6, or 11, will also be a solution. See, what's 11 squared? 11 squared is 121. If you divide 17 into 121, How many times does this go? 7 sevens are 49, 109, 2. Leaves a remainder of 2. So 121 is also congruent to 2 mod 17. So that's an example of this rule. What's a prime that's not congruent to 1 or 7 mod 8? I don't know. Well, p equal to 5. 5 is not congruent to 1 or 7 mod 8, and x squared congruent to 2 mod 5 has no solution. And there's one more rule about quadratic residues, which is very important. I'm just going to state it, and I'll prove it later. Quadratic reciprocity. So we have P and Q odd primes, not the same. So P over Q, this says, this is the Legendre symbol. This is P a quadratic residue mod Q or not? You can also ask, is Q a quadratic residue mod P? So quadratic reciprocity says P is a quadratic residue mod Q, and Q is a quadratic residue mod P. Both happen if and only if either P or Q, either P is congruent to 1 mod 4, or Q is congruent to 1 mod 4, or both, and P over Q is minus Q over P. One is P is a quadratic residue mod Q if and only if Q is not a quadratic residue mod P, if and only if P and Q are both congruent to 3 mod 4. So this is a very powerful rule that will allow us to compute Legendre symbols. And we'll see that on Wednesday. Okay. And that's all we're doing today. So see you later in the week. Any questions before I stop?
So we have class on Wednesday and next week, right? We have
Right.
class-
I think we have how many more classes? We have a class when I think the last class is a week from today, December 11th. So we have 2 more classes after today. And all we're going to be doing is studying quadratic residues and learning how to calculate them.
That's the last topic, right? We learned.
Yeah, this is the last topic.
Okay.
Okay.
So after 11, we'll be doing review for the finals.
Yes.
Okay.
Okay. See you
Thank
later
you.
this week.
Okay, bye.
Bye.